So last time I talked about 3D joints, and we didn't get time to do an example problem. I gave you a link to a couple example problems, but I thought we should at least do one in class. So let's say we have a plate. And there are two hinges, so like pin joints. One is at that side and one is in the middle of the back. And the dimensions this is 0.7 meters. This is 0.4 meters. This is 0.2, 0.4, and that marks a connection point for a cable. So the cable supports this thing. Okay, so the one connection point is on the plate, and the other one is on the wall. And the last dimension we need is this, and that's 0.45 meters. And this pin joint here produces thrust. That's a pin joint with thrust, and the other one doesn't. And we want to know what are the cable tension and the reaction loads at the joints. Oh, we need a mass too. Let's, how big is this thing? Let's make this, so the mass is 80 kilograms. Yeah, it's pretty big. So, well, let's see, 0.2, 0.3, 0.03, 0.003. I think that's reasonable, but it's heavy. So 0.7 times 0.28. No, 0.7 times 0.4 times 0.05, say, times 7,000. Yeah, so if it was steel, 5 centimeters thick, so pretty thick, that'd be 98 kilograms. This is 80 kilograms. It looks pretty heavy for the way I drew those hinges, but that's just because that's the only way I know how to draw hinges in 3D. So think of them as stronger. All right, well, the first thing we have to do is choose a coordinate system. Usually on 3D problems that I get out of textbooks, the coordinate system is chosen for you. Let's do one where the x-axis comes out this way. The y-axis goes this way. And the z-axis goes up. Check to make sure that those all satisfy the right-hand rule. It does. And so the origin is in that back left corner. And let's start with a free body diagram. So we have a weight force acting down at the midpoint. We have a cable tension acting on the plate going towards the wall. And now the joints, these two pin joints. So these are the complicated ones. They can apply either, so the one without thrust can apply either two forces or two forces in two couples. And the one with thrust can apply either three forces or three forces in two couples. Are we going to include the couples on this one? No, that's right. Because we have the two joints acting along the same axis. So this one, we have force components like this. I'll call that RBX and RBZ. And then for this one over here, this one provides thrust along the z-axis, in this case, along the axis of the joint. So in this case, that's the y component. So I'll just call this RA. It has all three components and no couples. This weight force is 80 times 9.81, so 784.8. And let's label these points and come up with some coordinates for these. So I'm calling this A. I'll call this B. C, I guess, is center of mass. We'll call that C and call this D. And let's come up with those coordinates. So the point A, that's at the origin that I chose. So coordinates are 0, 0, 0. The point B, what are the coordinates for that? Well, it's 0x and 0z, and it is half of 0.4 in the positive y direction. So that's 0.20. And C, that has a y component of 0.2. What's the x component of the center of mass of that plate? Yep. So 0.35x, 0.2y, 0z. And then the last one is D. That's still along that center line. So the y component is still 0.2. The x component is 0.45 now. And now we can start to fill out the table. So rho, force, and then moment. What do you want to compute the moment about? Well, the most unknown forces act at A, so that's usually as good a choice as any for the about point. So I'll start with the force RA. What's the about point? Yep, zeros. So now Cole doesn't have to answer any of the harder questions. He answered the easy one. That's what you get for sleeping. Now the hard questions come, and now you're going to have to ask it, and he's going to be back there with his feet up, sipping a margarita, etc. Okay, so the force is RAX, RAY, RAZ. Cross product is 0. And this is 3D, so remember that the moments all have 3 components. Okay. Now we'll go on to RB. One thing about, I happen to choose my about point to be the origin, which means that the rho vector is the coordinates where the force is applied for all of these. So this is going to be 0, 0.2, 0. The force vector, we only have an x component and a z component. So RBX, 0, RBZ. The x component is 0.2 RBZ. The y component is 0, and the z component is negative 0.2 RBX. And then we have the weight force. The rho vector for that is the coordinates where that force is applied, so 0.35, 0.20. The weight is 0, 0, negative 784.8. Can someone take that cross product for me?
Zero, negative 274.68.
Something went wrong there. It should have x and y. It should have x and y components and not a z component.
I put the y.
Oh, okay.
Negative 156.96.
Okay.
274.68.
Okay. And then the last one is the cable tension. That one's going to be a little bit of a pain. Let's get the row vector first. That's 0.45, 0.20. And now we have to think about how to represent that force. What we want is a force with a magnitude of T in the direction pointing from D towards the spot on the wall. Oh, and I didn't name that. I guess let's call that E, you know. So going from the point D to the point E. You with me on that cable force? Sometimes it's a little hard to picture these in 3D. So let's come up with the coordinates for E. So for the X component, it's going to be 0. For the Y component, it's going to be 0.4 plus another 0.2, so 0.6. And for Z, it's going to be positive 0.4. So how are we going to come up with a force vector with a magnitude of T that points from D to E? That's what we need. So the way to do that is to come up with a unit vector in the direction from D to E, and then multiply it by T. So to get that unit vector, let's think. So I'll say first, here's a vector that's in the direction we want. It's not a unit vector yet. And that's just going to be E minus D. So 0.6, 0.4, 0, minus 0.45, 0.20, and oh, thank you. 0, 0.6, 0.4. Okay, so the vector is negative 0.45, positive 0.4, positive 0.4. And now we need a unit vector in that direction. And so I'll write that like this. Does any of you guys have a calculator that'll just do that unit V command? Can you just tell me the unit vector in that direction? Otherwise, we just have to divide by the magnitude.
For negative 0.623, 0.553, 0.553.
Okay. And now, so the force applied by the cable is this unit vector times T, so negative 0.629 T, positive 0.553 T, positive 0.553 T. So put that in the force column. And can someone take that cross product for me? Everything has a T, so you can just do the numbers and we'll just multiply T's to everything. Does that alarm tell you when your cross product is ready? Like a microwave?
I don't think that's what it is.
It's 0.22, negative 0.25, and 2.76.
T. All right. Table's ready. So now plug it into Newton's laws. So I'm going to first use Newton's second law. It says RAX plus RBX minus 0.629T is equal to 0. That's the X component. And then the Y component says RAY plus 0.553T is equal to 0. And then the third one, RAZ plus RBZ plus 0.553T is equal to positive 784.8. And now the moment equation. Point 2 RBZ plus 0.22T is equal to positive 156.96. The Y equation says negative 0.25T is equal to negative 274.68. And then the Z component says negative 0.2 RBX plus 2.76T is equal to 0. So what we're doing here is adding up all those Y components and setting them equal to 0. And then I move the constant to the other side. So it says 274.68 minus 0.25T is equal to 0. I didn't count up the number of variables, but you can tell it's probably worth making sure always that you have the right number of variables for the right number of equations. So how many variables? We know we have 6 equations. How many variables do we have? We have 6. So unless something, one of these equations is a linear multiple of some of the other equations, we'll be able to solve this. So now let's write out the augmented matrix. we need 7 columns and not 6. And 6 equations. So here are the 6 equations. And the variables, let's go R, A, X, R, A, Y, R, A, Z, R, B, X, R, B, Z, and T. And then the last one is for the constants. Can somebody read me off the coefficients of these variables? So for the first one, 1 RAX, and then next one is RBX is 1, right? And then what else? Anything else? Negative 0.629, and then everything else is zeros. And the second equation? Okay. 0.553. Everything else 0. Okay, third equation.
RBZ is 1.
Okay.
RBZ is 1.
Okay.
T is 0.553. Constant is 74.8.
All right. Equation 4.
RBZ is 0.2. T is 0.22. Constant is 156.96.
Okay, equation 5.
T is negative 0.25. And the constant is negative 274.68.
All right. And 6.
RBX is negative 0.2. And T is 2.76.
Okay. All right. Can at least 2 people plug this into reduced row echelon form?
14471.
Okay, hold on. Let me.
And it's
So
in just the order that you put it in. So.
that's right. So this is RA that we're doing first. So sorry, read that to me again.
Negative 14471.24.
0.24.
Yes. And then
1, 4. Okay. We don't have any forces that big, do we? Something's going crazy with that. You have other components that big?
Yeah.
I think maybe that didn't work out. Yeah. If someone gives confirmation, I'll take it. Okay, so can you read me those answers again? Negative 14,000. Okay, and then Y? Okay, 0 basically.
I got negative 607.
Negative 607?
Yeah.
Okay. And then Z? Okay, 15,462? 162. Okay. And then 0. And then what for Z? And then T is 1098.
That's supposed to be 0? Oh, okay.
Oh, yeah. Okay, so we have a big negative X force on A and a big positive X force on B. Let's think about this for a second. So a big negative X force on A is like pulling it back toward the wall. And a big positive X force on B is pushing out. And so it's trying really hard to rotate it this way, which is because this big cable tension force is trying really hard to rotate it the other way. So let's think about the magnitude of those couples for a second, the magnitude of those moments. This would be like about so let's think about it about the z-axis. So RA and RB, let's say that those are each 15,000. So it's going to be, the distance between those two is 0.2 meters. And 15,000 times 0.2, it's going to be about a 30,000 Newton meter moment. 0.2, not 2. So 1,500 Newton meter moment. And the moment produced by that cable tension is going to be about 500, right? Because well, the moment arm is this. So how far is that? .45. Let's just double check a couple of these answers, because that still doesn't look right to me. You know, because think about like what the yeah. So, but like first of all, the thing that seems weird to me is these gigantic X forces, and those are going to produce. So that makes me think like let's think about the V component of the moment equation, And so if this one's pulling back and this one's pushing forward at 15,000 newtons, and those are 0.2 meters apart, then that couple is going to be about 0.2 times 15,000, which is 3, which is 3,000, right? 0.2 times 15,000, 3,000. And the only thing that can counteract that couple, that can counteract that moment, is the moment produced by that cable tension. So if that is a force of 1,000, it would need a moment arm of 3 about the z-axis to counteract that moment. You know what I mean? Are you following? And there's nothing on the scale of 3 in this problem. So that can't happen.
This doesn't look too different than what you got in the book.
Is it because the RAX and RBX are in opposite directions, they kind of cancel out?
That's what makes them a couple. And so, yeah, so that's how they're producing that moment together. Yep. In the book, it's a different problem in the book, I think, because I just made this up this morning. And so this cable tension would have to produce a moment about the z-axis that's equal to 3,000, you know, in the other direction. And that's not possible because the force is only 1,000. So there's no moment arm of 3 anywhere in this problem, you know, there's no distance that's anywhere close to 3. So let's calculate these moments again. So that force, so first that force, our point E is, so point E is 0x, 0.6y, 0.4z. That's what I have. And the point D is 0.45x, 0.2y, and 0z. Okay. And now, so if you subtract them, you get this. And I'm just going to do that real quick. So yeah, that moment arm is, well, it looks like it should be 0.622, but that shouldn't make that big a difference. But this should be 0.622.
Different.
Mm-hmm.
Some of us check that.
Yeah, I will. Okay, so 0.45, 0.2. So I'm getting, yeah, I'm getting, and you can see this is where that big problem with the z moment comes in. There's a big change in the z and some other changes too, but so for x, it's 0.111, let's say. For y, it's negative 0.249. And for z, it's 0.373. Okay, everything else, if we keep it the same, I guess the one thing we need to change is this should be 0.622. And for equation 4, this should be 0.11. I'll just leave it all in two decimal places. 0.5. For equation 5, we get negative 0.25 and then negative 274. And then for equation 6, we get negative 0.2 RBX, positive 0.37 T, and then 0. And so what changes for 1, this should be 0.622. For 4, this should be 0.11. Five stayed the same, and then 0.2 and 0.37. Okay, let's do this again. Okay, let's call that good. Yeah. You got what? For the first one? Okay. Let's call that within our round off error.
I got the same answer as you. Yeah, but only using the 2 decimals.
Yeah. Changing the decimal, like rounding can give you a couple percent error, no problem. That'll happen for sure. And like, for example, this 3.29, that really, if we kept all our digits, would be 0. Yeah, right. But if you're getting getting forces that are, let's say, 10 times bigger than any input force in the problem, at least consider the possibility that something went wrong, that's what it can happen. You can devise problems where, if I had made that cable go a mile out to the right, I mean, not a mile, but like way far out to the right, and put those two pin joints really close together on the other side, you could come up with a problem where even with a small applied external force, you got giant reaction forces, but it definitely raises your eyebrows, you know what I mean? Okay, any questions about that? Okay, remember the good stuff, forget the bad stuff, and then that's how you do 3D problems, though. Okay, talk to you Wednesday.